Hey guys, this is Mrs. Phipps, and welcome back to Physics for Everyone. Now, pre-AP Physics, talking about Newton's third law. We just talked about Newton's first law. We've also covered force basics, including free body diagrams, types of forces, and weight and mass. So make sure you can still do those three things. We're working on first and third. So, yeah. Sorry, I was looking at my recorder thing for just a second. All right, let's keep going. So Newton's third law is what we're talking about. And we got 4 questions we want to have answered. What is it? Do the forces cancel out? Why or why not? I'm picking how I want to do this. What is action-reaction? And what is the difference between force and acceleration? All right. So first off, these are going to move funky, so I'm going to erase them really quick. Okay, so what is it? Newton's third law, we already remember this, y'all have heard it before, is that for every action, there is an equal and opposite reaction. Okay, all right. So basically, a force is an interaction between 2 objects, okay? And the thing is, what's not in that statement that we occasionally need to remember is that there's always more than one object in this. You cannot, all right? You know that old thing, what's the sound of one hand clapping? You don't know? For there to be a one hand clapping, you have to actually interact with something. So if we've got to interact with something, that means there's 2 objects and 2 forces. Let's go ahead. We're going to take this and we're going to bump it up just a little bit. So for every action on an object, okay, I might some of this stuff in different colors, there is an equal in magnitude. So the size is the same and opposite in direction, because it's a vector, reaction on a second object. Okay. So we've gone for every action. For every action, there is an equal and opposite reaction to for every action on an object, there is an equal in magnitude and opposite in direction reaction on a second object. That's our basic law. So things we got to get from this is that we can get in here is we can come in here that there are always 2 objects, always 2 forces, and it's a vector because we have magnitude and direction. Okay, those are the things we can grab from there. Now, here's another question. So something comes up. So if I push on you and you push on me, why don't our forces cancel out, right? Okay, because if you think about it, how the heck does anybody ever win a tug of war if there's equal and opposite reactions? All right, so here's why. I think I mentioned in Newton's first law that first law, and we're going to discover second law pretty soon. First law is always based on one object. So first law is all the forces acting on one object. Okay. But third law is different. Third law is a pair of forces acting on 2 objects. So this is how you can tell if you're dealing with a first law problem or a third law problem. If they're talking about how things relate to one object, it's a first law problem, most likely. Or if it's 2 objects, it's a third law. So let's take a little bit about this, about how and the reason why things don't cancel out. Okay, I'm going to use the idea of a tug of war. All right, so we got a tug of war. In this tug of war, we've got people. It's kind of small tug of war. Okay. Okay, we got somebody pulling. Here's another person who's pulling. Okay. And on the other side, we have other people pulling. Change the pin. With a weird shaped head. Kind of a small person right there. And what happens is we've got this rope between them. All right. So where are action reaction stuff? So right here, where this guy touches, all right, so he is pulling backwards with the force, right? And the rope, by definition, so what are our two objects? We have the person and we have our rope. So there's our two objects. So the person pulls on the rope, okay, person on rope. And the rope pulls on the person. Okay. All right, look at how I changed those words around. So the rope on the person, person on the rope. Now, if you remember from your definitions of types of forces, tension tells us that if this rope, whoops, wrong button. If this rope, where's what I want? I'm not trying to move it. Tells us that if this rope is pulling with a certain amount of force on this side, then the rope must also be pulling with the same amount of force on this side. Okay, so we've got person on rope, rope on person, and then what's going to happen? This guy has the rope pulling, and which way is he going? This one's going here. All right, and this one is going here, and basically they're all pulling with the same amount of force, right? So why don't they cancel out? Because they don't. Hang on. Because they don't. So the reason why they can't cancel out is because of the idea of a system. All right, all of these guys in here, they're all pushing. All right, this is our system. All right, so they're all pushing however you want to. But the thing is, sorry guys, I was interrupted. So we're talking about why the forces don't cancel out. The forces don't cancel out because they're acting on a separate object. Yes, there's all these force pairs happening and everything like that. But if we were to go ahead, and I'm going to erase this circle real quick. We're going to say, okay, so why does one side win and the other side lose? It's because even though all those force pairs are acting in there, okay, when it comes right down to it, the way you win is what are all the forces that are acting on that object I just circled? Okay, so what's acting on the objects they just circle is, we'll use the other one because we can see it better. Okay. All right, just like we do a free body diagram, what are the forces that are acting on that system? The only forces that are acting on that system are the force of the rope pulling, and because we're going to be on a floor, we'll have a force of friction. All right, force of friction going this way, and we'll also have what? The pull force of all the people. So if one side's, so in other words, you win a tug of war because the net force acting on one team is bigger. That's about it. So you got between the tension over here, the tension pulling one way, the applied force pulling this way, and the friction force, which is going the wrong way. Why is it going the wrong way, guys? It's going the wrong way because if they're moving, that means friction acts this way. All right, so if the net force, all these forces here, okay, all these forces, the applied force of the pull minus the friction force minus the force of tension on this one side right here, on this side, is greater than the force of tension on this one. Okay, so yes, equal and opposite forces on different objects, but things move because of the net force on one object. Okay, next up, let's talk about action-reaction. So you heard me talking about the person on the rope, rope on the person. Action-reaction, first thing is just naming the forces. So if I hit a ball, hits the ball, what happens? What's the reaction? The ball hits the person. Can't spell. Another one would be, let's see, common one. If I'm swimming, right? Let's see, the hands push on the water. Hands push the water which way? Forward. Okay, what's the next batch? Then the water pushes hand backward. Let's see how the patterns going here? Okay, other one would be thinking, how does a car ever move? Okay, what does a car do? The tires, go over here then. Okay. So the tires push the road, right? And then finally, what does the road do? The road pushes the car. But which way, all right? So if the road pushes the car, that's the part that makes it go forward, right? So then which way is the tires pushing on the road? Backward. Okay, so in terms of our action-reaction, makes it a little bit smaller. Here's what we're looking for. Look for these words. Action, action-reaction, objects, action-reaction, forces. So action-reaction, person hits ball, ball hits person. See the pattern? Hand pushes water forward, water pushes hand backward, tires push road, road pushes car. Kind of like what we did here. Rope on person, person on rope. So in short, it follows a format all the time. It follows a very simple format. Okay. Object 1 on object 2. And then object 2 on object 1. So you should always be able to tell these things because there's always just the same two objects. So that would be our action-reaction objects, and then the force is what happens in between, okay? So yeah, like if I push on the desk pushes on me, all right? The force of me pushing on the desk, the normal force of the desk pushing on me. Kind of keep that one in mind. So it's action-reaction pairs, and here's something else. You think about which one happens first, okay? So go back to the hand hitting hand, right? So if I hit my hand, all right, my right hand goes to hit my left hand. Which one hits first? Okay. Well, here's the thing. Forces aren't based on time. Forces are snapshots in time. So all you're doing is this part. You're only looking at this part. So which one hit first? All right. Can my right hand hit my left hand before my left hand touches my right? It's impossible. So action-reaction is really a kind of a misnomer, because it's not one then the other. They always happen simultaneously. So kind of keep that one in mind too. Last thing we got to talk about. Okay, the difference between force and acceleration. All right, so you've got a football game. And so you've got two people. And you go, so this person I can't draw. All right, one of them has the ball. And here comes the other person. All right, and they're running to intercept. I'm sorry, running to whatever. I'm losing my football words. All right, and then they collide. Okay, and say if this one has 240 pounds, and this one is 175 pounds, who hits who harder? The 240-pound guy or the 175-pound guy? Think about it. Think about it. Which of you said 240 pound? You were wrong. The answer is they hit the same. All right, hit the same because, Isabel, because of equal and opposite reactions. The force of person 1 on person 2 is equal to the same force of 2 on 1. The reason why this works the way it does is because the reason why you have problems with this is because when we see things hit, we tend to think that the heavier one hits harder. The reality is they're always going to hit the same. Take the idea of a bug hits a bus, right? Okay, last thing, and I'm going to hurry because people are standing outside my door. Okay. If a bug hits a bus, which experiences more force? All right, they experience the same force. So what's different? Okay, like I keep saying this, the same force, but we know that something's different. The bug's dead. The car's doing the same thing. So what's happening here? Okay, what's happening is this. Okay, so if what we've got here is the force of the bug on the bus is equal to the negative force of the bus on the bug, what is different? The forces are the same, so what's different? Let's think about we've kind of learned a little, we kind of know a bit as well. We know that force is mass times acceleration. Okay, so if you've got a bug on the bus, well, that bus is a really big mass. So its motion doesn't change a lot at all. On the other hand, our bug is really, really tiny. Okay. As a result, it has an exceptionally big acceleration. So the forces are the same. The problem is on an everyday thing, we see things hit and we say, oh, they hit hard. But the reality is we're not seeing force. What we're seeing is acceleration. We're seeing the change in motion of the two objects. And the smaller the mass, the bigger the change in acceleration. All right? The bigger the mass, the smaller the change in acceleration. And I'm going to leave you with a joke. What was the last thing the bug saw as it hit the windshield of the bus? Its butt.